Gasoline at 20 degrees C is pumped through a smooth 12 centimeter diameter pipe. It's 10 kilometers long, and it has a flow rate of 75 cubic meters per hour. The inlet is fed by a pump at an absolute pressure of 24 atmospheres, and the exit is at standard atmospheric pressure and 150 meters higher. What we want to do is estimate the frictional head loss. So before we get into the energy equation, let's draw our free body diagram. So I have a very long pipe, and I have a pump at this end. And the height difference here is 150 meters over a 10 kilometer distance. Now I'm going to draw my free body diagram here. Now, I know the pipe is being fed at the inlet by a pump at 24 atmospheres, so I'm actually going to draw my control volume so it's right after the pump. The reason I'm doing that is I have no idea what the input of the pump is. I know what the output of the pump is, and that's 24 atmospheres. So here's my 0.1, here's my 0.2. So now that I have that together, we can start putting together our equation and make our assumptions and whatnot. So the first thing that I'm going to do is let's write out those assumptions, because I do want to use my energy equation. And let's make sure that my assumptions will work for it. I'm going to assume a steady flow. I can assume a steady flow because I'm given a flow rate, and there's no, if you look at the flow rate, there is no change of time per hour. Yeah, it's flowing at 75 cubic meters per hour, but it's not saying that it's flowing at 75 times T or some time component in there. So it is a steady flow. I'm going to assume a incompressible flow. Liquid gasoline is pretty much incompressible. I'm going to assume a constant temperature flow because there is nothing there that really says anything about temperature, so it's probably a pretty good assumption. I'm also going to assume no shaft work within the control volume. Because the way I've got it drawn, there's no pump, no turbine. So no shaft work. I could say no pump, no turbine. I could leave this one out and just cross it out when I do the equation, but I just want to get it there in the beginning so we're thinking about it. Okay, so what does the problem give me? Well, the problem tells me that I've got a flow rate, so I know that's Q, 75 cubic meters per hour. I know that P1 is 24 atmospheres. P2 is 1 atmosphere. I know the diameter of my pipe is 12 centimeters. Now I have gasoline at 20 degrees C, so I can go look that up. The density of gasoline at 20 degrees C out of the book will tell you 680 kilograms per cubic meter. Tell you a specific weight of 6,670 newtons per cubic meter. And if we want Z1 is 0, Z2 is 150 meters. So that gives us all of our starting information for the problem. So let's write down the energy equation. Full bore. Pressure over gamma plus V squared over 2G plus Z. It's all of that coming in. This is going to equal to all this stuff coming out. And it's going to be plus the head of the turbine minus the head of the pump plus the head of friction. So the first thing I usually like to do with the energy equations, knock out the low-hanging fruit, because it's 9 terms and we typically aren't going to be solving all 9 terms. Head of friction, that's what we're solving, so that's going to be there. But I know there is no pump and there's no turbine. And that's due to assumption 4 that I made, which is no shaft work, or we could just say no turbine, no pump. I'm going to set Z1 equal to 0, because that's where it's going. I do know Z2. I do know pressure 1 and pressure 2, so they're all there. So the last thing I have is my velocities. Well, this is where I can use if I exploit my idea of conservation of mass, what does conservation of mass tell me? It tells me that Q in equals Q out, or the mass flow rate in equals the mass flow rate out. And so that's Q. What is Q? It's V times A in is equal to V times A out. And so as we look at it, it's a 12 centimeter diameter pipe straight through. So what is the area coming in? Well, it's pi over 4, 12 centimeters times squared. Coming out is pi over 4, 12 centimeters squared. It's the same area. So if the areas are equivalent, that tells me the velocities are equivalent. If they're equivalent, I'll be able to subtract that from both sides because V1 is equal to V2. And there, right now, without actually starting the problem, we've now reduced a 9-term equation to 1, 2, 3, 4 terms. And so now let's just rearrange this for the head of friction. So HF, we'll leave that on one side, is going to be equal to P1 minus P2 divided by gamma plus Z. Actually, no, minus Z, because that's on that side. And we have to move that over. Yeah, so let's plug everything in. 24 atmospheres. Oh. 24 times, what is atmospheric pressure? And actually we can make that a little bit simpler because it's 24 minus 1. So we can just say 23 atmospheres. It's a nice thing about them being in the same units. So I've got 23 times 101,300 pascals, or newtons meter squared. We're going to divide that by the specific weight of the gasoline, 667 newtons per cubic meter. And then we're going to subtract from that 150 meters. So if we do that, we will calculate out the head of friction is going to be 199 meters. So that's how much frictional losses that we have in the system as it's going along. One thing to notice with this problem is the pipe length made no difference to the problem, because that's all buried into this term. It's all buried into this HF number. There's a lot of things that are hidden in this term, and we're going to spend a lot of time breaking that apart and calculating out, okay, how do we find HF if we don't know everything like we knew here?